Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer those questions at the end of the session and to follow up with any unanswered questions by email. As I suspect you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about the fundamentals, the related technology, and certainly the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I'm once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technologies, Shaun has been with the Quantic TRM company since the early or late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. Happy to. So today we're going to talk about beamformers and specifically about going through the process of trying to define what beamformer is the best for your application. Beamformers is kind of a very high-level collective term that we use for a variety of types of components, and really we're going to go through what that all means, and then really talk about the process of what we need to do and how we need to interface between a component manufacturer like Quantic TRM and our customers, and to try to go in there and really just go through the process and give some food for thought as to what sort of applications and what sort of solutions are the best things for those applications. And then we'll wrap it up with a summary and go through some Quantic TRM differentiators.
Okay, so to get started then, what is the best definition of a beamformer?
All right, so beamforming is at a high level definition, it is a device that takes a variety of signals, divides and combines them to create a unique phase or amplitude taper. Now that's a lot of words. So what it does is it vectorially sums RF signals directly in real time. The result of that vector summary will then be used to either feed an antenna or an aperture, or to take a signal from the antenna or aperture and then decode it back. So they create phase tapers and amplitude tapers that allow an antenna, for example, a flat or a linear array, to point in a specific direction. We know that if you feed an antenna or an array with a uniform illumination with an equal phase, the beam will be directed perpendicular to the surface of the array, basically look just straight overhead. You can steer that beam or have the main lobe of that beam focused in really any direction that you need based on the phase and amplitude taper that you send to those elements. So it doesn't necessarily have to look just in one direction. We can change that. You can also go in there and you can change some of the other parameters, such as side lobe performance, by adjusting the illumination factors of what's going on there. You can also go in there and subtract and create some difference patterns. And there's all kinds of other beam configurations that can be generated through the use of a beamformer. You can also use these beamformers to either use as a combiner or a divider using either a common antenna for multiple transceivers, or the other way around if you have multiple transceivers going up to different antennas. So there's a lot of things that can be done that all fall under this big global umbrella of beamforming, and it's once you start digging into it, the levels can be quite deep. So we have to make sure that we really understand really what it is that we're looking for. The other nice thing that we talk about here with a lot of the things that Quantic TRM builds, we focus in our business primarily on building passive beamformers. These beamformers are reciprocal devices, which means they work just as well for transmit as well as receive. They're also, from a power standpoint, very efficient. So that adds a lot of advantages over many active technologies. So from an efficiency standpoint, passive beamformers certainly have their advantages in the field.
Got it. And I understand that beamformers typically need to be customized. What's involved in that process?
Yeah, so custom beamforming is something that virtually all beamformers need to be customized in one way or fashion or another. Basically, because you're trying to feed a unique aperture for a unique application, therefore the network that feeds that antenna to generate those beams needs to be adjusted accordingly. So things, for example, like you have to look at how many antenna elements that you're going to have, what size that your array is going to be, what sort of beam widths do you need, how many beam states do you require to fulfill your final mission, and also how are we going to feed it? How many radios are involved? What sort of frequency and bandwidth are going to be required for all the different applications? These things here that all adjust the electrical circuits of what's going on inside the beamformer. Then we move into the environmental packaging. The physical form factor of the aperture itself will drive a lot of the geometry and the interconnections that work between that aperture and the beamformer itself. So very often there's a customization of the mechanical packaging, even if it's a similar sort of electrical circuit with something else that we've done in the past. Very often we'll have to go in there and modify that just to have the layout work. And then, of course, there's the whole environmental piece, whether this is going on an aircraft or going on a ground-based system. Those sorts of packaging requirements will vary dramatically. So once we get all that sort of information in, we could then say, okay, this is the sort of topology that we need going forward. And then we can then go ahead and start working up some of the circuit trade-offs that we have going forward. It's a very involved process. However, the more open communication we have with the system designer and the end use needs, the better we can tailor these sorts of ideas to make sure that the beamformer that we ultimately end up delivering is the best one for the system.
So you've mentioned trade-offs here. Can you share a little bit more as to the various considerations that are associated with the customization process?
Sure. So, at a real high level, what I just talked about really are more the system level stuff that really kind of dictate, where we start on the map. What we have now for solutions for that, for example, we can build custom amplitude and phase tapers for some of these beamformers. Say, for example, an equal illumination for a phased array will generate antenna patterns that'll have, the first side lobe will sit at about, say 13 dB down below the main lobe. Many applications, that lobe needs to be down below 20 dB. And one way to accomplish that, of course, is to apply a amplitude taper across the aperture to adjust those side lobe levels. So we can go in there and modify the amplitude taper on any of our beamformers to be able to accomplish that. Another thing that we have to look at there is there some sort of conventional sort of mounting that has to happen? The beamformer that's on the screen right now, you'll see that this here was used in a very unique application where we had to put the mounting screw locations not in the corners where they typically are, but in towards the middle of the part. And as a result, we had to work around those mounting locations for the individual circuitry. Bandwidth is also another big player here. The number of sections that we need to apply for all the circuit elements in there will drive bandwidth as well as insertion loss. Is there high peak power? All these sorts of things go in there and start really driving what the circuit design really needs to be. And again, the better communication that we have with our customer and the end use, the better sort of options that will become available. Most beamformers do have a very eclectic sort of mix of components. It's not unusual to have both, magic tees or 180 degree hybrids, 9-degree hybrids, directional couplers, power dividers, all integrated into a single package to end up with the particular mode and beam states that the antenna aperture requires in order for it to do its to work properly in the system. So there's a lot of things going on here, and we really have to make sure that we really understand what those trade-offs are, and then we can implement those in circuits. Hence the reason why these beamformers almost always tend to be custom designs. TRM does have a couple of generic designs for these sorts of beamformers, primarily in Butler matrices and monopulse comparators, because those tend to be a little bit more standard, and I'm going to use air quotes here for standard. But most of the time, because of the environments and whatnot, we do end up going through and doing some modification to those as well.
Okay. And how about some of the most common applications for beamformers?
Sure. So really, we go in there and we do an awful lot of different configurations. Like I said, I just mentioned the Butler matrix. Butler matrix is a sort of again sort of a quasi standard sort of circuit configuration. What it allows you to do is it allows you to generate the same number of beam states as you have elements. And each beam state is in a nice controlled phase progression, so that if you have a standard sort of layout with half wave spacing between your elements, you can generate 4 orthogonal beams that will progress nicely across the hemisphere. The one that's on the screen is a 4x4 Butler matrix. We also build these as 8x8. We have designs going up to 32x32. So there's a lot of sort of different variety that can happen with this sort of configuration. These are really useful for a variety of applications if you're trying to limit cost of a system, still have you cover hemispherical sort of coverage, as opposed to an active circuit. These do give you fixed beams as opposed to a beam that you can scan infinitely. So that is kind of a downside, if you will, of this sort of technology. However, what this does do from a power standpoint, these are far more efficient than any active array will ever be. And in addition to that, from a cost standpoint, these are far more cost effective doing that. So as long as we can have the limitation of having a fixed beam over an infinitely variable beam, a Butler matrix is a great solution for a wide variety of applications.
I see. Now, you mentioned a few minutes ago monopulse comparators. Could you explain a bit about those?
Sure. Monopulse comparators are a sort of antenna feed network that are used in tracking systems. That's primarily the application that these sort of circuits do get used in. And basically, if you look on the lower left-hand side of the screen, there you see an antenna element configuration. And this is very often used with either a reflector antenna, or it could just be something else where we're trying to track the source and make sure that we're always on the peak of that beam to get the best signal coming in. So what happens here is that if you have a four element antenna array, a stack 2 over 2, that square element array is then fed into the 4 inputs of the Butler matrix. What comes out of the Butler matrix is the sum port, which is basically all 4 of those antenna elements are summed or added together, giving you and all the energy that is being received comes out the sum port. The delta elevation and delta azimuth ports give you the differential of the phase in those 2 vertexes, and by doing that, you can have your control circuitry set up there to look for a null on both delta L and delta as while looking for a peak on the sum port. And by doing that in a tracking loop, you can ensure that the antenna will always be pointed directly at the source. And this is critical for any kind of tracking application, whether you're just making sure that you're getting the best data rate coming down off of a satellite, or if you're tracking the location of an incoming threat. The sort of positional accuracy is key to making sure that the system operates optimally. And this sort of device does that all in real time. There is no lag, and it does a very good job of providing that function for tracking systems. Again, just another application of a passive beamformer that Quantic TRM builds routinely.
Well, good information as usual, Shaun. Can you summarize?
Sure. So basically, beamformers are devices that that add and subtract RF signals in real time, and as a result, you can create unique phase tapers and amplitude tapers to manipulate energy coming in, to either add energy in one direction or subtract energy in one direction, to be able to go in and optimize your signal in any one place. There are multiple types of circuits that we have that do this, and there's a lot of different circuit configurations that fall under the broad beamformer category. Basically, when we go to create these custom beamformers, what's important here is to understand what's the system requirements are, and then from there we will then determine the architecture that is required to generate that, and then also taking all of the environments and other parameters into consideration while we're doing that design. So as a result, virtually all beamformers end up being customized in some fashion going forward. The two applications that I spoke of today, and these are by far not the only ones. There are many that we can go through, but two of the ones that we find that are the most popular are the Butler matrix, which generates a series of simultaneous beams, as well as the monopulse comparator, which is used for tracking systems. So those are just two applications. There are lots, and we enjoy building them all. It's always a challenge.
Okay, well, thank you. And as a custom manufacturer, what are some of the differences or differentiators maybe that you talk about with respect to Quantic TRM?
Sure, and I'll tell you the big differentiator here is the fact that we want to work with our customers to provide the best solution. When you're coming up with a beamformer, it is critical that there's a good conversation back and forth to make sure that the part that the customer is buying will indeed fulfill the needs of the customer. Because if the end customer doesn't get a product that they really need, it doesn't do anybody any good. This is just how we do business. We like to work with our customers to make sure that what they get is what they need. We like to think of ourselves as an extension of our customers' engineering team, bringing our expertise, merging with their expertise to create the best system possible. As we go through there, we utilize not only electrical designs, but also mechanical designs, robust mechanical packaging, material selections. That becomes especially critical if you're dealing with some very severe environments or parts that are going on a spacecraft. Those sorts of material selections are critical. We also have our own in-house testing facility, so we can provide objective evidence to make sure that we meet all the parameters that the system is required by doing this sort of work essentially in-house. Therefore, that service becomes a part of the data that gets supplied to the customer, and that gives you the objective evidence that what you've asked for is what you're getting. Bottom line here is that Quantic TRM is a solution provider that also provides hardware. So if you're looking for a beamformer or other sort of component where a not quite standard part is what you need, we like to work with you to supply that part to you. Not saying that we won't supply a standard part as well. We do those as well. But really our forte here is really working with our customers to provide custom solutions for unique applications.
Well, thank you for that good summary. And I think we do have time for at least one question. And the one that I have here, I understand that Quantic TRM works with a lot of different technologies, strip line, microstrip, and so on. Is there any one particular technology that aligns with beamformers, or what's your thoughts here?
Yeah, so the thoughts are that all of the above work very well with beamformers. And that really comes down to, again, part of the electrical and mechanical trades that need to get made based on the performance parameters. Some of those parameters are decided for us based on the frequency of operation. For example, if we're dealing with a very low frequency beamformer or component, it will more than likely be a lumped element sort of design, wire wound transformers with capacitors and resistors. As we go up in frequency, that will then more or less morph into other sorts of designs, whether it be strip line or microstrip. Certainly, a lot of beamformers use directional couplers and hybrids. Most of those are designed in strip line or suspended strip line, coplanar waveguide. Those sorts of components, depending on what the insertion loss requirements and physical packaging requirements are. So, depending on the exact frequency and the application, any or all of the technologies that we use here at Quantic TRM can be used and are used as part of beamforming networks. So the answer to your question, Paul, is all of the above, and it's and really any one of those can be used and will be used as part of a lot of these beamforming and mode forming networks that we build going forward. Just as a caveat, also, just as a reminder, Quantic TRM does build in virtually every technology except for waveguide. It's the only technology that we don't build in-house.
Okay, very good, very good. So I guess in summary, the bullets on the screen here really sum it up nicely. If you are a customer and you have additional questions, we would love to hear from you. You can call our engineering hotline. The number is on your screen, 888-677-6877. There is no cost associated with these calls. And if you are one of our field sales representatives, you know your calls are always welcome, and you can get additional information through the rep portal. Looking ahead, our next Tech Talk will be on Tuesday, August 27th, and the topic will be Space 2024. Thank you again, Shaun, and thanks to everyone for joining us.
Yes, thank you.